Dear lecturers, participants and guests of the 4th Spring Nobel Festival, a world of exponential innovation, Sakensi Folin Kazakh Agritechnical University, the general partner of this event, is hosting this year's festival. For 65 years of its activity, KATU has trained more than 70,000 specialists, successfully working in all major sectors of the agrotechnical sphere. Among the ranks of our graduates are deputies of the Parliament of the Republic of Kazakhstan, heads of leading enterprises, nationally known public figures, and athletes. Today, our university is one of the leaders of the national higher education on the national rating of the demand for higher education institutions of Kazakhstan, from the IAAR on the quality of educational programs. And also, KATU is the base university for digitalization of agricultural production in Kazakhstan. Our partners include more than 160 world-renowned leading research universities and research centers. Among them are the University of California at Davis, which is the second highest institution in the world of the agricultural industry, Agro-Polytech University in Europe, and many others. Today, KATU has started a dual diploma education in 3 specialties jointly with the University of Milan in Italy, which gives our graduates the opportunity to receive diplomas from 2 countries. Our university offers the opportunity to study at bachelor's, master's, and doctorates. Currently, the number of students exceeds 12,000, of whom 70% are studying under the state grants. There is a full opportunity to study in the military department. All necessary conditions are created for them to be qualified specialists. The university aims for a seamless experience in any format of education. For students, there is a printing office and a library equipped with an electronic system that has more than 1.5 million book collections. As Kazakhstan's leading university in the agricultural sector, we are speakers at the session of the Spring Festival represented by the chairman of the board of KATU, PhD in economics, Kairat Kaparovich Aytuganov.
Alimjon, you can start.
Hello, dear participants. We welcome to unique online platform for discussion and knowledge exchange with Nobel Prize laureates, outstanding scientists and experts. Thank you for your attention and interested in your annual festival. We express our special gratitude for organization of this festival to the Kazakh Agritechnical University, named after Sakensi Folin. And today, our presenter, David Jeffrey Ullman, welcome. Today, the main titles and the discussion topics, it's what is data science? The main problems, today we will discuss the main problems and the main aspects and the position rules data science today in IT. Professor, can you continue and present your lecture?
Thank you very much. Okay, I want to thank the organizers of this Nobel Fest. It sounds like a great opportunity, and I hope. I will try to talk a little bit about as was just said about data science. Before I do, though, I will hope you'll join me in a prayer for the Ukrainian people who are right now being murdered daily for no good reason whatsoever. I hope that stops very, very soon. Anyway, wait. Share screen. Okay, this should do it. Okay, good. Okay, anyway, okay, I want to talk a little bit about data science and its relationship to really everything else that goes on in computer science. And I thought I'd start by sort of giving you a little picture of how I see data, computer science as a whole structured. This is not going right. No. Okay. Anyway, many people will divide computer science into a hardware branch and a software branch. I'm going to talk about software, obviously. That's where data science largely fits. Let me just mention one thing about hardware. It's changed quite a bit recently. If you look 20 or 30 years ago, really all you needed to know was the Intel, what's called x86 architecture. All computers, basically, or almost all computers were built using the same architecture. More recently, the architectures have become very much branched in many different directions. In particular, there are lots of specialized processing chips. You've probably heard about graphics processing units, perhaps tensor processing units, FPGAs. There are a number of very interesting specialized architectures that are coming along, often designed to support AI applications, but not exclusively. Another thing which is, I think, very interesting about the hardware world is that processor speeds have pretty much stayed the same for many years now, but networks, that is communication, is speeding up very rapidly. And the result is that where people used to talk about supercomputers, these giant machines that were designed for very typically numerical computations. Now you just rent 10,000 processors on some computing cloud. I think the age of the supercomputer is really finished. Well, when you talk about software, you again generally divide software into two kinds. There's system software, that is the internals of computers, and then all the applications. Now, system software, 40, 50 years ago, it was all compilers and operating systems. Those are the major system components that people had to learn about. But that has changed. Again, networks are very important. Obviously, the internet is part of everything. Computer security and cryptography, which is one of the key components of a computer security solution, obviously very important. Privacy. And I'm going to include databases. Now, the first database systems really came along very shortly after the first compilers and operating systems. But database systems in particular have also had a major evolution. Again, 20, 30 years ago, the only thing of interest in database systems was the relational model and the SQL programming language. And the applications were largely business data processing. More recently, I think it's become far more than just SQL programming. For example, there are architectures for database systems that didn't exist 20, 30 years ago. For example, sometimes it makes more sense to store a relation by column than the more traditional storage by row. Really big database systems are distributed over maybe very large computing clusters. They're way too big to live at any one processor. The applications, again, are I think, very exciting. A company like Amazon that does its business on the web, they basically live in it. They basically are a database system. Moreover, a lot of machine learning, the most exciting parts of it, involve managing the biggest data sets. That is, sometimes you spend weeks running through one of these monstrous training sets in order to build a model. Anyway, we'll talk about that. Okay, so applications. Again, there's a view. When I was breaking into the field, maybe, I don't know, 55 years ago, applications were about inventing algorithms to do this and that. Well, it's still about algorithms, but the data, it's not just algorithms, it's how you apply the algorithms to the data that is very, very important. So data has become at least an equally important component, I think, of applications. And obviously, many of the new and really exciting algorithms are in the machine learning world or artificial intelligence more generally. Okay, so here's how the applications break down. There are, of course, there are applications still that are not AI, not machine learning, not. And I'm going to give you one interesting example at the end of this talk. Okay, so let's see, artificial intelligence. Well, again, this is something that has itself changed recently. It used to be thought that artificial intelligence was about simulating how people reason. Well, I mean, that's sort of what the name artificial intelligence means. But what artificial intelligence really turns out to be is solving some of the most complex applications, very often, but not always, using machine learning. Just to give you an example, in the older artificial intelligence approach, one of the things they did was build what they call expert systems. You have some special purpose language that lets you write sort of logical rules. So if you want to build in the old way, if you wanted to build a system that would control a driverless car, you'd have experts pumping in rules. Here's a kind of a trivial example here. If you see an old lady crossing the street, then the car should stop. Okay, hard to argue with that. The trouble with these expert systems, if you have 3 rules, you can probably look at them and kind of figure out what they are doing and what the consequences are. But a real expert system, for example, for medical diagnosis, would involve millions of rules. Now, when you have millions of rules, no one can understand whether they are sound when they act together. Each rule by itself, you might say, yeah, it's correct. Yeah, I agree. But they can have all kinds of crazy unintended consequences. Nobody can understand who's responsible. When something goes wrong, which rule was it that caused the problem? Now, as a result, for example, even though in principle an expert system can do better medical diagnosis than your typical doctor, no one ever really used these systems in practice. The newer approach, though, would be, they are teaching cars to drive themselves. And the way they do it is by developing data. Okay. These cars go, in our neighborhood, there are a number of driverless car companies, and you see them driving all around our neighborhood. And they have sensors, and they're learning what it is that's out there, and how cars behave, and just how to do the right thing. And this is the modern approach, and it seems to be working. Okay. Even today, while these driverless cars are not perfect, they are better than your typical human driver at not having a road accident. Okay, so as I've sort of hinted, machine learning is sort of at the center of everything, but machine learning has also changed its meaning. If you go back 30 years, let's say, the idea was that machine learning was about software that sort of taught itself. That is, as it was running, it would improve its performance based on its experiences, and finding out when it went wrong, it would improve. In fact, modern machine learning is very much different. It's simply building models of something important. For example, you want the machine to diagnose tumors. So you give it data. You show it, these are tumors, these are images without tumors. And the system learns from the data, but it doesn't improve its performance unless you give it new data, and that's up to you. You have to find the new data, and you retrain the model. Let me give you a simple example. The modern electronic mail systems. I was thinking I use Gmail, but it's typical of any of these large scale systems. They pretty much identify spam emails. And the way they do that is by getting data. That is, they ask you to report any email that you see in your inbox that you regard as spam, and everything that's not reported will be assumed to be not spam. So it has a big training set, that is lots and lots of examples of spam and lots of examples of not spam. Okay, what that gives a company like Gmail is a training set, and because spammers are always trying to find new ways to attract attention and trick people into answering their emails. They'll change what they do pretty much every day. So a system like Gmail has to every day develop a new training set. And but the software itself isn't learning. It's just being retrained on more up-to-date data. Now, just to give you an idea, what is a model is really an algorithm that will look at an email and tell you, is this spam or not? So a very simple model would be to go through the training set and find words that appear much more commonly in spam emails than in others. My favorite example is the phrase Nigerian prince. I wonder, since I'm talking to people around the world, whether you get these kinds of spam emails, or whether there is in fact some perhaps equivalent but different approach. But I would before I had Gmail to filter out the spam, I'd get these messages that would say something like, I'm a Nigerian prince and I have $50 million that I want to get out of the country. And I'm happy to share it with you. Wow, $25 million for me. Sounds great, Oh, and then it would say, but I need a plane ticket or something. So please send me $1,000, and when I get out of my country, I'll come and visit you, and I'll give you half of my money. Yeah, well, fortunately, I never fell for it, but I do know people who did, and lost. Obviously, they keep the $1,000. They never show up. They don't have any hidden money. Okay. Okay. At any rate, that's I guess neither here nor there. But if an email says I'm a Nigerian prince, it's probably spam. Okay. So anyway, so the model would be would just be a list of words that indicate spam, and the algorithm that would use the model would simply say, if an email contains one or more of the words on this list, then I'm going to declare it spam, and otherwise it's okay. Obviously, the models that are in use today are much, much more complex than this. Okay, so let's, again, I'm trying to sort things out. So there are three terms, AI, artificial intelligence, machine learning, and data science. And it's very common that these terms are confused, or people think that they really mean the same thing. Okay. I'm going to argue that they're all different. Okay. First of all, as I said, machine learning is a body of techniques for building models. So again, some very powerful techniques. Okay. AI these days is the application of techniques such as machine learning, but others as well, to solve what you might think of as the core problems of computer science, the problems that don't pertain to any one application. We have a couple of examples. Translation from one natural language to another. Great, a great application for which much progress has been made, but almost everybody needs language translation. I assume I'm being translated right now, right? Perhaps by a machine. Another interesting example of these chatbots. These they're algorithms that let you type in a natural language, tries to understand what it is you're asking, and give you a useful response. Again, the technology that's pretty much in its infancy, but looks very interesting. Intrusion detection, that is monitoring the internet or computer systems to notice that something is that shouldn't be allowed to happen is happening. Anyway, there are many examples of core problems in computer science. Interestingly, artificial intelligence is now even going back to compilers, and then there are people who are trying to write compilers that sort of use machine learning to decide on how to generate code. Anyway, data science, again, is sort of the parallel to AI. It's typically the same collection of techniques, but with the express purpose of creating an application to some particular problem in, say, science or commerce. Again, let me remind you that machine learning it's very popular. It's very important. I don't deny that. But you hear the people basically treating it as if it were all that's what data science is. Well, I have a couple of problems with that. Okay. The first objection is that what is machine learning community claims ideas that really predated it. Example, clustering. Mathematicians were looking at clustering algorithms long before there was anything called machine learning. Gradient descent, again, it's mathematics. I think it really comes from Isaac Newton, if I'm not mistaken. Association rules, another example of a model a model making system. I'll talk to you about this in a second. That predates the machine learning community. The second problem, I think quite obvious, is that to assume that it's a mistake to assume that every problem in data science can be solved by creating a model. I'll give you. I'm going to close the talk with an example of one such. And the third is that sometimes understandability counts. The problem is that machine learning, the most powerful techniques in machine learning give you models that you can't understand. They do what they do. They tend to do the right thing, but you can't explain what it is they're doing. Just to give you an example of explainability, it's association rules, really a simple idea. It dates from the last century, the end of the last century. Association rules are really they're just if-then rules about sets of items that cause effects. The original idea was simply to look at what people bought together when they would go to a store, and they would bring a market basket to the checkout. The checkout register, and the store could determine what it is people bought together. So, for example, people who buy bread are more likely to buy butter because butter goes with bread. You probably don't need a whole theory to discover that, but they were more complicated examples of stores were able to sort of understand what people would buy together, so they could group them together on the shelves and increase their sales. As I said, it comes from the 1990s, and it comes out of the database community. The machine learning community had nothing to do with this. Well, let me just give you an example of how you would apply association rules to discover phishing attacks. Well, you can think of any email as a basket, just like the market basket. And in the basket are all the words that appear in that email. And if you look for combinations of words that appear most commonly in spam emails, you might discover that the words Nigerian and Prince together imply that this is a phishing attack, spam. Well, the fact is that this method is it's not bad, but it's not that great. Even a simple machine learning model, like learning a positive or negative weight to put on each word and declare that an email is spam if and only if the sum of the weights exceeds some threshold. That will be a couple of percentage points more accurate, at least. The trouble is, association rules are understandable. So if you actually happen to be a Nigerian prince, and you find that any email you send out is classified as a spam, I can show you the rule that says, well, you use the words Nigerian and Prince in your signature or something, and therefore it was declared to be spam. Sorry about that. Now, in comparison, for example, Gmail allows you to point to an email that it has classified as spam and answer the question. It'll answer the question, why is this spam? Now, sometimes there's a special reason, but most of the time, what it says is something like this. It says, it looks like other emails that people said were spam. Now, what that really means is that this is declared to be spam because it matches whatever model it is that we have today, and it's much too complicated to explain to you, so just trust us. Okay, now that's okay. I mean, Google does do a pretty good job of identifying the spams and letting the non-spams go through. The trouble is, sometimes understandability is rather important. So for example, insurance companies try to estimate the risk, that is, figure out the appropriate premium for you to pay. Based on your, certain characteristics. So if it's health insurance, it wants to know your weight, your age, and many things. So if they suddenly raise your premium, you should have a right to have them explain to you why they raised your premium. But what they're just going to do is say, well, we developed this new machine learning model, and that model said you are a big risk, so we're charging you more. So I thought I'd just try to lay out these subjects in a Venn diagram. First of all, there's computer science. And then there's domain science, the applications, whether it's physics or medicine or commerce. And in the middle is data science somewhere. Machine learning is a part of computer science. It's not all of computer science, probably not even as big as I've shown it here, but I needed to have room to write machine learning. And some of data science involves machine learning. And then there's mathematics and statistics. And then I have to apologize. I had to draw these bubbles much smaller than they deserve, just to avoid overlaps that I didn't intend. But what I'm trying to express by this is that if you want to study computer science, you want to do data science, you need to study mathematics and you need to study statistics because they impact computer science, including machine learning, in many important ways. But they don't deliver to data science except through computer science. That is, the algorithms that come from the mathematics and the statistics are the things that actually solve the data science problems, not the math or statistics directly. Okay, well, again, I just want to close the story by talking about an example of what I consider an algorithm in data science that is not machine learning. It doesn't involve the creation of a model, but it's very clever and it has a lot of very interesting applications. It's called locality sensitive hashing, or LSH. I thought I'd just give you a plug. I give myself a plug for a book that I wrote a number of years ago with Yuri Leskovich and Anand Rajaraman. I don't feel guilty mentioning this because it's published by Cambridge University Press. You can get a free downloadable copy and you can see the URL there. Okay, and it covers a lot of different data science ideas, including the one that I'll talk about now, and including machine learning. Anyway, the problem of locality sensitive hashing is you need to find the similar items in some large set. And the large set, it could be 1 million, could be 100 million, could be 1 billion items. And you want to do it without looking at all pairs of items, because if you think about it, there are just too many pairs to even spend a few machine instructions per pair. Now, until you see the tricks, this looks like black magic, right? Because it lets you see the similar pairs, and you never have to look at most of the non-similar pairs. That's the only way you can get around the problem of there being a quadratic number of pairs, where a quadratic in the number of items. So I'm just going to give you a really basic example of how this thing works. It's the problem what's called entity resolution. We're given a set of records, and let's say the records have a name field, maybe a phone number field, an address field, maybe some government ID field. And our goal is to try to find those records that refer to the same person. For example, a credit rating agency, they get hundreds of millions of records a day, and they have to figure out who each record is talking about, because you don't want to have your credit rating lowered because somebody with the same name did something bad. Anyway, it's a little tricky. I mean, if everybody in the world had a unique name and records always spelled those names exactly right, no typos, no nothing, then it would be quite easy, right? You just take a look at the name, and if two records have the same name, then they're the same person. If they have different names, they're different person. But in fact, it's a problem. Sometimes there are typos. Sometimes, if you have a middle name or a patronymic, sometimes it's included, sometimes not. You can have the same person can have their name appearing in many different ways. And of course, there's somebody in the world who has exactly the same name as you. So just because two records have the same name doesn't mean that they're the same person. Okay, now again, even 1 million records, and 1 million is not a big data set, let's say, compared with what a credit rating agency has to deal with. Well, a million choose 2 is about 500 billion, or 5 times 10 to the 11th pairs of records. So if I have to do 5 times 10 to the 11th anything, it's going to take me a lot of time, or a lot of machines, or both. It's going to be a very hard problem. And of course, if instead of 1 million records, I have 1 billion records, it's just astronomical. There's no way I'm ever going to be able to do that. Okay. Well, anyway, the trick behind locality-sensitive hashing is that you avoid looking at all the pairs, or in fact, most pairs you just don't look at at all. But you will miss a few. As you get a few what are called false negatives, that is, pairs of records that should be merged because in truth they do refer to the same person, but you don't. The LSH algorithm will not see them and will not merge them. So the trick is, we need to invent a number of different hash functions. A hash function, remember, is going to throw items into buckets. And each of these hash functions has the property that if items are truly similar, then there's a good chance that they'll wind up in the same bucket, or at least the chance is much, much greater than the chance they'll wind up in the same bucket if they are not similar. So if they're not similar, they're not going to wind up in the same bucket almost 100%, but not quite 100%. If they are similar, there's some reasonable percentage that they will wind up in the same bucket. Now we're going to use more than one hash function. So you use hash function number 1, you throw everything into buckets, you look at the items that appear in the same bucket. You then hash using hash function number 2, new buckets, a new set of buckets. And again, you look inside each bucket, you compare only those elements that are in the same bucket. You take a third hash function, you do the same thing with a new set of buckets, and so on. So for coming back to our example of entity resolution, one simple hash function would be just look at the name field, and you have one bucket for each name. And so records go in the same bucket if and only if they have identical name values. So again, if the records represent the same person, there's a fairly good chance that they will have exactly the same name. And there might be a misspelling or some confusion about a middle name or something, or even the order of names. So they might not go in the same bucket. And of course, if you and someone else have exactly the same name, you might wind up in the same bucket as them, and you get compared. Well, your records get compared with their records, even though you're not the same person. The comparison should determine that no, these are not the same person. But it's work. You have to work inside the buckets. Well, you might then, for a second one, you might pick the phone number, and again the same thing. Phone number might identify the same person, but sometimes people will share a phone, so you just two different people have the same phone, or you used to have that phone and you gave it up, phone number, and you gave it up, and now somebody else has your phone number, or there's a typo. They have a number that's one different from yours, but some clerk entered it incorrectly, and your phone number appears in their record. Could happen. And then you can address and various ID numbers and so on. So again, our prayer is that if two records do represent the same person, they'll be identical in at least one field. Not a guarantee, but but you hope that at least one of these hashing functions will put them in the same bucket, put those two records in the same bucket. Therefore, we'll compare them and we'll say, yes, these do represent the same person. And so we'll merge those records. You hope, again, that different people don't agree in any field, but unfortunately, sometimes they do, again, like two people who have exactly the same name. So I tried to imply. Hello?
Sorry. Микрофон выключил ма?
А я думал, ты на наурыз.
Нет, нет.
Извините, можете выключить микрофоны? Sorry, can you continue?
Хорошо. Yeah. Anyway, again, if two records wind up in the same bucket, then the candidates, you still have to compare these two records and make a judgment. You sort of want to hope that they will at least be similar in most of the fields, even if not all. And for the reasons I've been talking about, you will get candidates that really represent different people, and you do need to discover that. Okay, so just to wrap up, okay, we're gonna the way you do locality sensitive hashing for entity resolution is you hash the records using fields like the name, phone, address, ID number, and so on. You compare what you really hope will be a relatively small number of pairs of records that get sent to the same bucket for at least one of these hash functions. As I said, the downside is, well, the upside is most pairs of records never wind up in the same bucket, and therefore you never even think about them. The fact is, you could have a pair of records that do represent the same person, but there's a little typo in each of the fields that you use for your hashing, and so they never wind up in the same bucket. They become a false negative, and you miss them. Again, hopefully that will be a very, very rare situation. Okay, and so with that, I will close. Thank you.
Okay, thank you for you.
I need to stop sharing. Okay, there we go.
Okay. We have some questions. It's very interesting lectures. Thank you for you, and more detailed information about structure of data science and how we can use machine learning, its examples, and the data protection and the web server protections and the hashing functions using in information security. It's basic of web technologies today. So thank you for this concentrated and the more information consist in this lecture. And some questions from participants. So you can ask your question or write for me on the chat, dear participants.
Yeah. Should I read the chat, or will you select the questions?
Okay. If you have questions on the chat, do you have questions on the chat?
All I see is some numbers. I do not see.
Okay.
It, but...
Okay. I have some questions. The first, it's what is the rule of metadates today and in the future?
I'm sorry. Could you say that again? What is the rule?
What is the rule of metadates today and in the future?
Well, I'm sorry. What is a metadate?
Yeah. So, which rule metadates today and the perspectives?
Well, yeah, but I'm sorry. I'm not understanding. Meta, you mean like what used to be called Facebook, or no?
Can you hear me?
Alimjon, could you explain the word metadata? He doesn't understand.
What is it? Oh, metadata.
Yes, exactly.
It's
Yeah,
date,
well,
about dates. So in the using in the
right. Well, you know, all databases have some sort of a schema. You have to explain to people what the columns mean, what the rows represent, and what the you know what the names of the columns mean, and so on. That I'm not sure that that's a really important issue these days. I mean, obviously you need it. I'm not seeing any. It does not seem to be driving the field forward, let's say, right now. I mean, you have to know. You have to know about it, and you have to use it. But I wouldn't spend too much time thinking about it.
Okay, thank you. So we have participants. Do you have questions on this chat? Okay, the next question. How to effective build in career in data science?
Again, say that again, please.
How to effective build a career in data sciences?
How to interview a candidate?
No, how to build a career in data science.
For junior programmers.
I mean, for someone for a job, right?
Recommendations and which part of data science learning, maybe some tracks of education or making of professional careers.
Yeah. Well, for one thing, I'd like to know that they have studied at least a little bit about what our business, whatever our business is. Okay, if for example, if our business is drug discovery, I'd like them to know some chemistry and biology and obviously. I would like, again, I'd like them to be skilled in mathematics. No question about that. If you have the basis of mathematics, you can learn the computer science parts. Okay, but these days, without a good grounding in mathematics, it's very hard to do the most sophisticated things. I would say.
Okay. So yeah, and the next questions. Yeah, it's very special question. So how will build career in data science? So it's need to define the first. I think it's directions of data science for protecting data science or improving data science, using data science in the web server or clusters, and then defining some types of dates using in the data clusters. So it's very special, and the track it's very sometimes different steps, including. So our participants have questions. So,
Okay.
can you ask?
May I ask? Is it possible?
Yeah.
Yeah.
Okay.
Go ahead.
Dr. Ullman, good to see you. Great
Yes.
to see you.
Hi.
I have a question. Why and how the term of data science is so popular today, despite the fact that all the scientific community used to work with higher mathematics, statistical analysis in their researches, for example? Why the term of data science so popular today?
Well, I don't know. When I was a young man, I was told anything that calls itself a science isn't. Okay, think about that. Physics doesn't call itself physics science. Chemistry doesn't call itself chemistry science, chemical science. It's only fake sciences that call themselves sciences. I don't know whether that's quite true, but there is a tendency to call everything a science rather than it sounds better than data engineering, let's say, which is sort of an older term. But in fact, that's what we're doing. We're engineering using data. So again, I don't know who was the first person to use the term data science. It seems very quickly to have taken over from earlier terms like big data. Right? Remember that everybody had to say they were doing data, big data, and then it was data mining. But again, like it or not, data science is what we call it, and it is a useful body of knowledge, and there are really good applications, and I think it's great if someone can learn the computing, the part of it that involves computing, and also learn the part that is an application area. It's very much easier if there's one person who understands both the computing and the application than trying to get a team of people, none of whom really understand each other and get to work together.
Thank you for the answer. I was curious about that because, as being a part of scientific research at the university, some people even do not realize that they are doing some kind of data science stuff using the statistical analysis, using some kind of probability in their researches and their proving. That's why I was asking about that.
No, fair enough. Good.
Okay, thank you for the questions. Participants, if you have questions, you can ask me or write on the chat. And the next question, it's my questions. So, every countries have e-governments. So, the next question, what recommendations you can give to improve e-government database of Kazakhstan? So, maybe technical recommendations, maybe directions of using artificial intelligence and the directions of using some special tools for improving some technological process or improving quality of services.
Well, I guess I would obviously have to know something about, first of all, what the status of your government software is right now, and where you wanted to go with it. That is what what would you like to see done with government data that is not now being done?
So the first, it's more recommendations today have for improving database or system, and more recommendations are oriented to the first. It's needed improving technical specifications and the more servers, more computational parameters needing improving. Some recommendations are oriented to extending database and optimizing structure of database. It's which recommendations it's good and how we will comparing the solutions. Maybe it's the first, it's the main problems oriented to creating new structure, oriented to fast operating of dates.
Well, again, you'd have to first tell me what does the government have in database in data, and what would you like to have them do with it?
Okay, yeah, it's a database today. It's oriented and based on the platform. For example, it's PostgreSQL database structures and the Oracle database using. So some platforms, every platform's databases have special requirements and limits of operatings per seconds, and it's very different today. And do you have maybe solutions or recommendations use specific platforms, for example, Oracle or other?
That's not your problem. Okay, whether it's an Oracle database or Postgres or MySQL or not an issue. The question is, what data do you have? What would you like to do with it? And then we can start thinking about how you do it.
So it's the first in developing process of governments. It's your recommendations need oriented of final elements. It's quality of services, yeah, and making services and analyzing all steps of operations in the services. I think it's.
Yeah. Well, but again, you see, you're not telling me what data the government has, and you're not telling me what you'd like to do with that data. Let's take an example. I assume people pay income tax in Kazakhstan, right?
Okay.
Okay. So they've got information about people's how much money people earned and presumably where they earned it. Okay.
Yeah.
And now, what would you like to do with that? Perhaps you'd like to detect.
Okay, I think it's oriented of users. I think it's oriented of users and how many operations we will run on this database and services.
No, but again, it's until you tell me how, what particular service do you want to provide?
Okay. I understand you, and it's a different position. We can visions of this question, and more parameters and some features needed defined pre developing process. So thank you. And the next question is.
Ask. Sorry for interrupt. I do have one additional question.
Okay.
Okay. Dr. Ullman, what is your personal opinion on data ethics in kind of data science or ML-based projects? Have you faced some governmental issues on that?
Personally, no. There are there are obviously many issues that governments are facing these days about, privacy, for example, is obviously a big deal. Just before I got on, I was reading an article about AI bias. I try to characterize machine learning as You take a data set, you use it to build a model. If the data set is biased, you're going to get a biased model. Okay, so for example, if a company, the companies these days, they get so many applications for jobs that they write a program to look at people's resumes and decide whether they're good candidates or not. Well, how do you decide whether someone's a good candidate? You'd better, you're going to use your own data, your own performance, the performance of your own employees to determine what characteristics make for a good employee. Well, if a company, let's say, discriminates against women, doesn't promote them in a fair manner, then the data is going to show that being a female is not, makes you unlikely to be a good employee. But that isn't true. It's the data, the source of the data was itself biased, so the data reflects the bias. If you use that data to build an AI, some say machine learning algorithm, that machine learning algorithm will be biased. How do you, I think that's one of the big ethical questions that has come up. But there's also, there are lots of issues in privacy, and I guess I am perhaps an outlier in this. My view is that our expectations for privacy need to change. 200 years ago, if you lived in a village, everybody knew your business, right? You couldn't hide from your neighbors. When people started moving to cities, and big cities, you became anonymous, right? You sort of developed this expectation that you could do things and nobody would know you were doing them. Okay. And as a result, we got this notion that you have an inherent right to privacy, that nobody should know if you robbed the bank, because it's nobody's business but yours. And I think that in a sense, the internet has placed us all in a global village where everybody knows everything about you. Okay. And well, for example, the European Union has this sort of right to be forgotten. If somebody said something you don't agree with on the internet about you, you have the right to force a company like Google to not show that. Well, I don't think you have that right. Okay, if it's false, then that is cause for a libel suit. But that was true 200 years ago too. If somebody, put up a piece of paper in the town square accusing you of, I won't even, just any horrible thing, and it was false, you had a right to redress. You still have that right to redress. But the right to conceal from other people true things about you, again, I'm not sure that we can retain that right any more than we had this right in a village 200 years ago.
Thank you.
I think that's a very interesting ethical issue.
Yes.
Okay, thank you. Today we'll look at the main opportunities in data science. Thank you, Professor. and it's limited time. So thank you for your presentation, and I hope today we presented information. It's very important, and it's basic for improving data science and the using in IT technologies. So it's very more results and good solutions. We can look in your publications and the lectures. Thank you for you.
Okay, well, yes, thank you. Yes, everybody, thank you very much for listening and for giving me this opportunity to speak to all of you. And,
thank you. See you the next time.
Right. Okay.
Okay, thank you very much.
Right. Goodbye, all.
Bye. Thank you.
Bye.